Okay, welcome back, everybody, to this morning session. So we are very pleased to have as a second speaker this morning Lionel Mason from Oxford, who are going to tell us about celestial symmetry via twistor actions. Please, thank you.
So I'd like to thank the organisers for allowing me to speak and letting me to come to this beautiful city and so on. After that last talk, I now feel rather intimidated with all that wonderful, beautiful physics and so on. Whereas here, this would be well, as Monty Python might say, and now for something completely different, something much more kind of mathematical. But this is part of the maybe it is part of the celestial holography sort of approach, but so this conference is somehow bringing together well, at least three and maybe more sort of strands with a real physicists as well. So the Corollian, the celestial, and here in my case, I guess more twistorial, and so the that they all center on the celestial sphere. I mean, in the Corollian case, though, we're looking for theories on null infinity that have BMS symmetries, and in order that you find something that's holographically dual to physics in the interior space-time. Celestial, of course, we're just really focusing on we're being less religious about the light cone of infinity, and we're just interested in the celestial sphere. So that celestial sphere could be at space-like infinity or related to both null past and future null infinity. And the relation between the two is really just to get rid of the R factor on the Corollian case and sort of put it somewhere else in the celestial case. Now, the twistor theory sort of sits very naturally on both, in relation to both theories, as I'll hopefully explain, or both approaches. First of all, twistor space sort of naturally kind of fibers over the celestial sphere. And in fact, it even fibers over null infinity. So twistor space, we'll see later, only has one extra coordinate over null infinity. So it does live there, but it sort of it knows less about the generators of null infinity than Corollian theories do. And in all three cases, though, we're interested in finding theories dual to standard conventional physical theories in 4 dimensions, such as gauge theory and gravity. And this talk is really going to be focused on the gauge theory case. And in that case, I'm going to be focusing on how to understand these higher celestial symmetries that have been discovered in recent years that now come under the name of the S-algebra. And so I want to give a unified approach to all of those and to try and sort of just triangulate how they fit into the 3 theories and how to understand them in a completely Noetherian way from an action and somehow something that at least a twistor theorist could have written down sort of, 50 years, well, I exaggerate, 20 or so years ago. Okay, so that's the general orbit of this talk. And I can't resist, though, just going back to some prehistory as to where some of these ideas come from, because, of course, that people were doing holography before holography became a big name. In particular, Ted Newman in the 1970s and on was trying to sort of rebuild physics in the bulk of space-time from null infinity. And so the idea was to say, well, okay, we can pose data at null infinity, but what about reconstruction of space-time? And the idea was that one can see the imprint of a point or an event X in the interior space-time via its light cone cut at null infinity. And if you were doing gauge theory, a simple thing you could do, well, we all know that sort of gauge theories are all about parallel propagation of internal vectors on a bundle, and you can propagate that vector all the way out from the spacetime event here to null infinity, and that would give you basically the information of the Yang-Mills connection in the interior of the spacetime encoded in this parallel propagator called capital F. And well, there's a certain amount of toing and froing between Ted Newman and the Oxford group. So Ted Newman was actually writing down differential equations for this light cone cut, so-called good cut equation. Roger Penrose then reinterpreted that in terms of the bulk of spacetime. Sorry, Roger Penrose reinterpreted his good cut equation as a story in twistor space. And the idea was that you could attach a twistor space to null infinity, and this good cut would then become a sort of just a simple holomorphic curve inside some deformation of CP3. Richard Ward then said, oh, I could do that for Yang-Mills too. Instead of deforming the underlying twistor space, you could deform a bundle over twistor space. And so then you could go back and you could find a version of the good cut equation for Yang-Mills. And the person who made this idea precise was George Sparling, and he wrote down the Sparling equation, which is the Yang-Mills version of Ted Newman's good cut equation. Now, so this is a remarkable thing, right? You'd have thought that the parallel propagator from the interior of spacetime out to null infinity would be a complicated object. It encodes the Yang-Mills field, but in a very messy way, and you wouldn't really expect it to satisfy any nice equations. But here, if you impose this Sparling equation, where A is the null data for the Yang-Mills field at null infinity, you can reconstruct the connection on the interior spacetime just out of its characteristic data at null infinity. But in this self-dual sector. And so this self-dual sector will be an imprint all the way through of the where life is easy in twistor space. And what we will see is that the self-dual sector is described beautifully holomorphically in twistor space, and that holomorphy underlies the complete integrability of the self-dual sector. And what we're hopefully going to see is that complete integrability is what leads to a recursion operator, leads to hierarchies, leads to hierarchies of symmetries. So that's okay. So the modern the modern history now, sort of this is now talking about the last sort of 20 years or so, is that we now have to set up theories in twistor space. These tend to have this sort of what's known as a holomorphic Chern-Simons form. So Chern-Simons, of course, you know the field equations tell you that a connection is flat. Here, holomorphic Chern-Simons tells you you're wedging it against a holomorphic volume form on a complex manifold. So what it does is it tells you your connection is holomorphic. And that allows it to contain full functional degrees of freedom, in particular of theories like Yang-Mills and gravity theories in the self-dual sector. And in fact, what we get is not so much, you know, supersymmetrically, you can express these things as Chern-Simons theory, but if you just want to work sort of standard Yang-Mills, QCD, or standard non-supersymmetric gravity, you end up with things that look more like BF theories. There's also some string theory ideas that have been very successful. And so these start sort of just over 20 years ago. And anyway, so we now, what they allowed us to do was to go beyond the self-dual sector. So we could find the full S matrices of gauge and gravity theories. And in fact, with the ambitwistor strings in all dimensions, it's not really, there's aspects of this which are dimension agnostic. But I'm going to focus more on the twistor actions, which are like string field theories for these twistor strings. And there's been a recent resurgence in ideas to do with the quantization of twisted string theories and twisted holography and twistor space and so on. So I'll only touch on some of these things, and I think Atul in his talk might sort of push some of these ideas further. Okay, so the structure of this talk then is that I want to sort of first of all review the developments from celestial holography. I want to review the celestial operator product expansions that lead to the S algebra, which is all the Yang-Mills version of the celestial symmetries. And I want to just review, at least briefly, how it is that these things sort of play a role in twisted holography of the form set up by Costello-Paquette, and also how they can be encoded in terms of hierarchies of charges at null infinity. And so then I want to explain how it is that these symmetries are the completely natural geometric thing that you expect on twistor space. On space-time, you know, well, okay, you write them down and they're big, complicated formulae. You're not quite sure why you should expect them. But in twistor space, they're just straightforward gauge symmetries. And in order to sort of generate them, you can sort of introduce some sort of recursion operator, which starts off with your standard favorite sort of large gauge symmetry. You hit it with the recursion operator, it turns into another one, another one, another one. You get a whole ladder of them. This leads to sort of hierarchies which are given by recursion operators, which are just differential equations on Scry that you could solve, but they'll appear algebraically in twistor space. The twistor actions then give rise to Noether, express them as Noether charges, and we can see how you can then get to conservation laws for the self-dual sector, but these will then become sort of flux laws when you go beyond the self-dual sector. There'll no longer be conservation laws. Yeah.
Poisson bracket, like algebra, or are these twistor? Do the charges live on twist? Like I know there's the flux laws, but I just want like the full charge. So
Sorry,
I know there's the flux.
I can repeat it. Yeah, you're asking.
There's the flux law, but could you also just have the full charge and the charges have a Poisson bracket that's like LW infinity, or like in space time or on twistor space, or?
So I mean, in the self-dual sector, you can do everything is symplectically equivalent. So that is to say, you could do the charges in the Ashtekar-Streubel symplectic structure, so to speak, or in the twistor one. I mean, they are equivalent.
So I guess I'm just asking for, like, it is true that in the self-dual sector there are space-time charges and they have this Poisson bracket?
Yes.
Okay, thank you.
Okay, and well, yes, and yeah. So well, we'll talk about how all these things fit together and give rise to things that you're maybe more familiar with on null infinity as we go. Okay, so to review the kind of where the celestial symmetries were first seen, this is actually a story that really comes out of the celestial holography program to start with, whereby you make the you express the hope, shall I say, that you can find a celestial conformal field theory at null infinity, so that a scattering amplitude in the bulk of space-time can be expressed as the correlation function of a bunch of operators in this celestial conformal field theory. And so there's what people sort of refer to as the bottom-up approach, where you just say, well, who knows, I can't write down such a theory, but what would it have to do to recreate the scattering amplitudes that we know and love? And so one of the strategies is to use the soft limit. So you write your momentum with an energy out the front, and then you've just got an extra complex parameter for the it's a null momentum, of course. So you just need a complex parameter essentially on the Riemann sphere to determine the direction of the momentum, and you can just expand in the energies to get this soft expansion. It's another way of expressing the Mellin transform well, you're just looking at the integer powers. And then in the celestial theory, the so-called splitting functions, which has been the bread and butter of amplitude's law, become OPEs in the complex variable Z. So as K1 becomes parallel to K2, these so-called splitting functions have been sort of, these are universal things which you can study, and they will correspond to the 2 points Z1 and Z2 becoming close together in K1 and K2, and they define that they would have to define an OPE for the J's, the currents that are meant to define the amplitude. And you can compute the algebra just from first principles, well, sorry, from the amplitude law. And this gives rise to what's now become known as the S algebra. So it's an OPE which basically just has the Poisson bracket and a 1 over Z factor in the normal way, as an OPE does. But then there's some sort of, you have to separate into modes in the Z tilde. And of course in the energy as well, you've already done that. So what you end up with is once you've done modes in the Z tilde and the omega, you get this commutation law that the well, I mean, so the R parameter is really just encoding the Z. So it's really what's non-trivial here is the P and the N. So okay, so this is a nice algebra. Well, I'll tell you later what it is geometrically. So in the world of twisted holography, then we could. This is more in the world of Castello-Piquet and Sharma and others, and you can introduce a J for the self-dual field, a J tilde for the anti-self-dual field. So we've got this S algebra here. It's encoded in essentially a vertex operator algebra for the J's. These act on the J tildes in the obvious way, but the J tildes sort of don't really talk to each other very much. But this is now a vertex operator algebra. You can do loop calculations, and you can start talking about this as being part of some celestial CFT. And the idea is that conformal blocks give rise to amplitudes. And this has done some sort of rather wonderful successful calculations along the lines of, for example, producing rational terms in loop amplitudes and things like that. So it doesn't tend to get beyond rational amplitude, so at least not so far. Okay, so this is sort of a review then of the S algebra and its connection with celestial holography. For the Carolian amongst you, or the people who like to live out at null infinity at least, these things have also had a realization at null infinity. So if you set up your usual Bondi coordinates then, with a retarded time u and a Riemann sphere parameter z on the sphere as infinity, then, well, so first of all, we'll go into some sort of Bondi-like gauge where the vector potential for the Yang-Mills field has vanishing u components, and then it splits into what are well known to be the self-dual and anti-self-dual parts. The self-dual being sort of perhaps slightly counterintuitively the anti-holomorphic part, and ASD the other way around. And it's well known that you can sort of pick out the self-dual, anti-self-dual curvatures and F02, and then there's really three components to the curvature, and these can be given in terms of other derivatives of the A. So these calligraphic A's determine everything in the asymptotic data of the Yang-Mills field. So if you want to actually sort of determine what the other components are from the characteristic data, you solve the asymptotic Bianchi identities. So with n equals 0, 1, 2, you can sort of go down this chain here, and you can find the rest of the curvature. And then after that, you can go on and try and compute the field in the bulk as well, sort of at least in power series form, by integrating equations that look a bit like this. And can you find charges that correspond to these S-algebra symmetries? So that was a question that Friedel, Pranzetti, and Reclario set themselves. They did it first for gravity, second for Yang-Mills, and then it was improved later, a couple of years later. And and they said, well, okay, so these we could carry on this kind of Bianchi identity. We just keep going. We're going to get sort of we'll call these these curvatures. So these are the anti-self-dual curvatures now, the F tildes. Notationally, this is just what it is. I'm sorry, the tildes come and go, and there'll be some tildes the other way later on. These are shifts in conventions here. So, well, this is to agree with the Friedel, Pranzetti, Reclario conventions. And so the you can build a sequence of RNs now, calligraphic RNs, which extend the curvature components at null infinity. And then what they managed to do was to show that you could realize the S algebra by introducing some rows here. So the rows, these will have spin S, and the R's have the appropriate weight to sort of be integrated against such things. And then this would generate the S algebra just under sort of Poisson brackets, and this is sort of what you might call a bootstrap. You know, they're saying, well, how do we go? We start off with something which does the ordinary gauge symmetry, and then we try and go further up through the list of S algebra charges. Can we sort of mimic it? And they sort of corrected as they went, and so on. And they got some complicated formulae. They sort of it's okay to start off with the regular charge that we know and love. At null infinity that generates gauge transformations, and then you can sort of hope to correct the rho 1 R1 with stuff to make it all work. So you get a formula that looks like that, and you correct Q2, you correct some more, and this takes you up the S algebra. Maybe this is the parameter P in the S algebra. You keep going up, and at some point it gets rather complicated, and you make some guesses and so on and hope for the best. So what this talk is about then is how can we understand this recursion and these charges as arising from first principles, and how do they relate to the J's and J tildes that Costello and Paquette sort of came up with. So so my claim is I can give, or we, sorry, this is work with Romain, Adam Kmech, and Atul Sharma. We can give a top-down derivation from first principles in twistor space, and one that gives a natural geometric interpretation as to what the S algebra is. Okay, so sorry, maybe I should ask for any questions at this point.
Could you comment about the non-locality?
Yeah, so of course, in doing this, we've had to solve a whole sequence of equations that look like this, and of course, so to obtain Rn, you need to keep on integrating up scry. So it's still local to scry. It's local to the initial data at scry, at null infinity, but so it's not it's not brutally non-local, but it's still quite non-local. And I guess one of the things I want to promise is that it will look local on twistor space.
So the recursion relation that you have of the previous slide, there are like self-dual equation, but is still like in gravity where they reproduce the full equation of motion of your theory until a certain spin, or like do they diverge, or do like when you look at the full equation of motion, not just the self-dual sector?
Right. So, I mean, I guess what this is doing is pretending that your anti-self-dual Yang-Mills linear field on the background is looking like a field that actually has arbitrarily high spin. That's what it looks like you're doing. So if you were to try and write down such an equation, you would do that. Now you can do that. You can integrate these equations. There's no obstruction to integrating these equations on a null hypersurface. If you wanted to do that into the bulk, there would be Book-Dull conditions. And so the way this acts on the full theory is still somewhat, yeah, these are, in the first instance, these are symmetries. These are exact symmetries of the self-dual sector, but we expect them to act on the S matrix, hopefully in an interesting way in the full theory.
Thank you.
Yeah.
Where is your surface S? Is that at the bottom of Scry, or?
Yeah, I mean, when we want to make contact with sort of celestial holography, you'll push that surface down to U equals minus infinity.
Well, but you would only expect to get the S algebra if it's at the bottom of Scry, right?
That's right. Yeah.
So,
but it's, yeah. Sorry. Yes. Go on.
So then U is minus infinity in these equations.
Yeah, you're going to push U to minus infinity. But these equations make sense all the way up and down Scry, and in the self-dual sector, I think they're reasonably well behaved. Yeah, yeah. Okay, so the first thing I want to do is to explain the S algebra geometrically, and that allows me to sort of introduce twistor coordinates as well, because the So the lambda coordinate is just going to be a fancy way of talking about the sphere. So the lambda coordinate is just homogeneous coordinates for the sphere. It's a thing that projected geometers often do. You want to allow z equals infinity, so you express it as a ratio of two coordinates, and you work in quantities that have some homogeneity in lambda. And but then I need to introduce two new coordinates, mu. And these coordinates nicely fit into the two indices. We had two integer indices on the S algebra. So one of them is the degree of the polynomial in 2p is the degree of the polynomial in the mu's, and then the m is the difference between the naught dot and the one dot components. So, and if you introduce these two coordinates mu naught and mu one in this way, then then the S algebra is just the algebra of functions with values in the Lie algebra here, and that's precisely all it is. That's so if you wanted to realize it geometrically, this is how you would do it. And in doing so, then what you've done is you've taken the Riemann sphere and you've just added, so that by the Riemann sphere I mean the celestial sphere, and you've added two extra coordinates. And that is what the S algebra is, just as an algebra. Now we can ask, but I want to take this space seriously. Usually we work projectively, so in projectivizing the Riemann sphere, taking out the scalings of lambda, we take out the scalings of all of these lambdas and mu. So this is actually a homogeneous polynomial, total weight 0. And so we think about it, this is defining coordinates on a projective 3 space, but because we've singled out this projection onto this Riemann sphere, we're not going to allow lambda to vanish, and so it's really projective 3 space minus a line. Okay, so that's some sort of picture of twistor space over the celestial sphere, and so we see this that the S algebra, but then how do we see it as something that might have something to say about Yang-Mills theory? So then we have to go back to sort of the Wall construction in 1978, who tells us that self-dual Yang-Mills fields are fields defined, well, so self-dual Yang-Mills fields, of course, are fields whose anti-self-dual curvature vanishes on regions of space-time. Here I'm thinking of space-time as being a little bit complexified, but don't worry about that. You can deal with reality conditions as you like. And the claim is that such things, such self-dual Yang-Mills fields correspond to holomorphic vector bundles over regions of twistor space, this CP3. And the image was that you would cover projective space by two open sets, just covering the lambda sphere like this, the celestial sphere. And so it's a space that's topologically non-trivial, but you could trivialize it, say, over the left-hand side of the celestial sphere or the right-hand side. And on the middle, there would be some sort of holomorphic gluing between frames on this side and frames on the other side. And this SW, if you go back, you see it has singularities, both lambda 1 equals 0 and lambda naught equals 0, but the it's nicely defined over the equatorial patch here, and that's what you're going to use to shift the patching and define a bundle on that space. So that was the Wall construction from well, approaching 50 years ago. And so that's the connection of the S algebra to Yang-Mills, or really infinitesimally, one should think of them as being gluons, and they will be soft gluons. So what you'll find is that they grow as you go out to infinity. The way that you actually construct the field on space-time is to represent points in the bulk of space-time by a line in twistor space via this instance relation. This is in some sense going to later be the lift of a cut of scry. And what you'll do is you'll try to find, so over a Riemann sphere, there aren't, if the bundle is topologically trivial, the bundle has to be analytically trivial too. And so you can find global holomorphic frames over the Riemann sphere. And this will play a role later. And this is the same as that sort of parallel propagator that sort of Sparling told us about sort of back in the 70s. And but Sparling's version was actually not sort of obtained from this kind of patching description I gave on the previous slide, but from what's known as a Dolbeau version, where you express holomorphy via a differential operator, a d-bar operator. So there you correct the standard flat d-bar operator, which is just d by dz bar, d by d mu bar. But it's correcting it with a naught-1 form A. And according to Sparling, that A could be the lift from scry of the asymptotic data. But here we can work more generally. And in fact, we will want to work more generally later here. So we could use any old naught-1 form with values in the bundle to deform the d-bar operator. And then this frame would satisfy this holomorphic equation, which is like now looking very much like George Sparling's equation for the parallel propagators out to scry. Okay, so I was really sort of saying all this to introduce sort of the next ingredients, which is a self-dual twistor action. So in order for this in order for this to actually define a holomorphic structure on the bundle, d bar squared has to vanish. If you want to have holomorphic sections of the bundle, you have to have a holomorphy of this connection, which is the integrability that d bar squared vanishes. And in order to do that, so this is the field equation then, that the d bar squared should vanish. And if you want to sort of impose that via an action, we're just going to do a BF trick. So what we're going to do is we have this A, so the self-dual Yang-Mills state was this 0, 1 form A, and we're going to introduce a B, which will be a Lagrange multiplier field. And so, so this will give us a holomorphic BF action. And the nice thing that comes out is that this Lagrange multiplier isn't just some weird Lagrange multiplier, it's something that you wanted. So the A encodes the self-dual part of the field, and what we're going to find is that the B encodes the anti-self-dual part of the field. And we'll see later sort of integral formulae that allow you to realize the anti-self-dual part of the field as an integral of B. So in order to reconstruct the space-time field from A, we've got to go through this kind of yoga that we had here, involving some trivialization over lines, finding this frame F, and then the F then, I forgot to say this part here, gives you a parallel propagator. So if you trivialize over this line here, trivialize over that line there, those two, if they intersect in a point W here, then the X1 and X2 will have to be connected by a light ray. And then connecting up these two Fs will give you parallel propagation according to the Yang-Mills connection up that light ray. Okay, so that's twistor theory in a nutshell. So, and this is the twistor action for the self-dual sector, at least, in a nutshell. So any questions at that point? All understood. Fantastic. So okay, so what are the local gauge symmetries? Well, it turns out that well, you expect. I mean, A is obviously it's in terms of being Chern-Simons, even if it's holomorphic Chern-Simons, A has gauge freedom of the form expected. And infinitesimally, you have chi, an element of the Lie algebra, and A will, psi is an element of the Lie algebra, and A will vary by d bar of some psi. And B, though, also has some gauge freedom. And so B, which is meant to correspond to the anti-self-dual part of the field. So I didn't say it very clearly, but this B has weight -4 to make this integral make sense. And so its gauge freedom has to have a different spin weight. This has to, or homogeneity weight, it has to have weight -4. But B has a very similar gauge transformation. So just it has its own one with the chi, but then of course the standard gauge transformations of the bundle rotate it as well. And so being a Chern-Simons BF theory, I'm sure everyone who likes sort of their Noether arguments for Chern-Simons and BF will have walked through the Noether theory for such theories. The symplectic form is just essentially sort of B wedge A or delta B wedge delta A. And so that's a symplectic form. And then if you want to do the gauge transformations, they have very simple sort of Hamiltonians here. And these Hamiltonians are nicely sort of exact. So, well, sorry. So here, this is the Hamiltonian density. So we're going to say that that it's essentially d bar of the these chi and psi. And they have the obvious Poisson bracket relations, which look actually very much like the ones that we had before for the j's and j tildes already. We're not quite there yet because these psi's and chi's are arbitrary gauge transformations. And one of the things that's a little bit off-putting is that we've gone from a kind of twistor space is really, as a manifold, it's a 6 real dimensional manifold. So we're happy about it because it's a 3-dimensional complex manifold, and we often like to work with holomorphic objects. But actually, it's, at this point, these gauge transformations are functions of 6 real variables. Anyway, but they have the right Poisson bracket relations. But the point is that if you want to think of these as large gauge transformations, there are only symmetries at the boundary if at the boundary of your sort of, so to speak, initial data surface, which we're going to think of as being out at infinity, these psi and chi are actually holomorphic. And if they're holomorphic, then they will reduce to functions of 3 variables, which is the right place for the S algebra. So, and then what will happen is that because the Hamiltonians were exact, the charge integrals reduce to integrals at infinity of this very simple form, psi b plus chi a, where psi and chi are the gauge transformations, and these are now have to be holomorphic in order to be understood as symmetries. So this boundary of the kind of what you might think of as the initial data surface on twistor space is now going to be related to some sphere at scry or spatial infinity times the Riemann sphere in twistor space. And so these will be integrated over a sphere in twistor space and so on. So we will now get a gauge algebra, and now because these psi and chi are holomorphic at the boundary, these can now be replaced by the S algebra that we found earlier. I mean, this can be thought of as a nice basis for the psi and chi. So this will now give you a Noetherian representation of the symmetry algebra associated with the S algebra. I mean, it's worth saying, yeah, sorry, Sarah. Was there a question? No. Okay. I've already forgotten what it was worth saying, though. Maybe it'll come back to me in a bit. Okay, so we can substitute in these psi's your favorite S algebra. Oh yeah, sorry. What I was going to say was that the psi times b are the standard gauge transformations for little a, and as I was saying before, you can, if you like, identify that little a with the asymptotic data of the gauge field. So you can think of these psi's, because B is conjugate to A, the psi's here as being generalizations of the standard gauge symmetry that you expect to have at null infinity. But the chi's are sort of new, and they came from the fact that we had this extra gauge freedom in the B. This adding on a d bar to B is a symmetry of this action. If you put it, because of the kind of Bianchi identity satisfied by this curvature, adding on d bar or something to B is a symmetry. So that's not visible on space-time in any normal way. Okay, so how does this relate to stuff at null infinity? Well, we can sort of talk about the projection to null infinity then, which requires some choices. We do the standard Z is just the ratio of the 2 lambda coordinates, and mu can project to the Bondi U coordinate here, but there's 2 components to mu, so there's also a fiber coordinate Q, which I'll leave like that. And if you do that, then we could certainly pull back the asymptotic data to give you an example of little a. But you don't need to do that. But that's just to emphasize that you can see stuff at null infinity in this. But the we can then ask, how do we get the anti-self-dual field out of the B data? Because the B and we have a simple integral formula here. So this, if you take the standard sort of Penrose integral formula at null infinity, for r equals -1, 0, and 1, that will give the components of the anti-self-dual field at null infinity there. But we can, following the FPR logic, we can just carry on having higher and higher powers of Q in this formula and get the whole sequence of charge aspects. Or is it lower and lower? Because, yeah. So, No, yeah, sorry, it's higher and higher. Sorry, yes. So, so what you discover is then that this is an integral formula for solutions to this equation, and this gives all of the RNs just in terms of the data B, and okay, so we suddenly see the structure that Friedel, Pransesi, and Raclerio discovered. And there's no need to solve differential equations now to find the R tildes. We just have to crank up this power of Q here. And so this is actually part of a theme that was discovered in the 1990s about sort of symmetries and integrability of self-dual Yang mills. So there's a standard story in the theory of completely integrable systems that that introduces what's known as the recursion operator. And so here, what's happening is you can start off with sort of regular symmetries. Here, just a standard sort of gauge symmetry at Scry, whose conserved quantity is the asymptotic charge, or maybe even the sort of more fancy singular ones that are holomorphic charge aspects. And you can crank it up by the recursion operator, and you get an infinite sequence of symmetries that start from some basic one. And so really that's what's happening here. And the Q multiplies the Hamiltonian densities and the charges. And so it is in some sense part of an old story. And yeah, so this gives rise to recursion. And you can understand this hierarchy. So these hierarchies were, so in fact, the way that the integral systems people would talk about it is that you start off with something like a translation, just a regular translation symmetry. You hit it with the recursion operator, and instead of being the spatial translation, it becomes the time motion. And then you hit it again, and then it'd be a higher time. And you hit it again, it'd be a higher time above that. And this was fitting into the concept of integrability, where you say you have infinitely many conserved quantities in the involution if what you had done was to start from a translation symmetry which commutes. You could start with non-commuting things, and that's sort of roughly speaking some of what's going on here. We're starting off with a charge symmetry which doesn't commute, and so we get higher symmetries based on that. And these higher flows can be generated from the twistor theory sort of semi-automatically just by introducing higher powers in there. Okay, so how do we actually get to the charges from Friedel, Pransesi, and Ricariu? Well, they needed to have this row here. Now, the rows were integrals times R, and we have to sort of somehow get that from our kind of S algebra generator. So in fact, what's happening here is that as part of the Penrose transform, or in this formula here, sorry, I missed out something. As part of this formula here, if you wanted to use the Xi charges, you would you'd have to unwrap by this frame here. The Xi charges were Xi times B, and you'd have to sort of unwrap by this conjugation with the frame as infinity. And then you would have to also sort of turn this expression here into something, you'd have to break up the Xi into functions of U and Q. And I realize what I forgot to say here is that you can use the recursion operator to get the conjugate charge aspects coming from the symmetries of the B. So these now are the conjugate R tildes. They start on the A, and they also satisfy recursion relations, and that follows in a very similar way. Okay, so you end up with what looks like a rather elaborate formula. And so one of the formulae then is turning one of these polynomials in mu's into something that just depends on U's and lambda tildes. So the rho is an object that lives on null infinity, and that is what's going to end up in the integral formula here on scry. But you have to do a certain amount of work to turn this into something that's going to live in twistor space, which is this psi tilde. And then this wedge condition that we had then was the condition this psi tilde is actually independent of lambda bar. But if f is non-trivial, that needs to be expanded, and that contains a lot of stuff. So we don't just need to do this operation, we also need to sort of conjugate with f. And so you need to solve for this frame iteratively. And that's what ends up giving us this translation from the twistor integral, which is just psi being a polynomial times b, into this rho n times calligraphic Rn. And you have very similar formulae for the conjugate charges. And then that now, if you expand this all out, you start getting these formulae which get more and more elaborated. Okay, so then you can get similar formulae for the conjugate charges now out of this framework. We know how to expand the f and get terms that look like these kind of U inverse derivatives of A and so on and so on. And then if we want to relate to Castello-Paquet, we've got to shift these integrals back down to minus infinity. So, okay, so sorry, I hope that wasn't over time. Well, okay. So any questions at that point? I hope I haven't. Okay, so just to conclude then, the wall construction, in the same way as the Penrose nonlinear graviton construction sort of tells you that the LW1 plus infinity algebra, which is the gravitational analog of this, corresponds to gravitons by the Penrose nonlinear graviton construction. The Ward construction tells you that the S algebra corresponds to self-dual gluons. Using the twistor action, we can construct sort of Noether charges and out of this symmetry algebra, and that comes in a very natural way because these things are just generating the standard gauge freedoms on twistor space, and the integrability of the self-dual sector gives rise to recursion operator, all these hierarchies of conserved quantities and flows for the self-dual sector. And as I say, things that people have been working on these things, I mean, since, well, before the 90s even, in the 80s. Beyond the self-dual sector, of course, these are no longer conserved quantities, and that there will be some flux laws. These will obviously go up scry. And with a bit of luck, I don't think they're as well understood as we'd like, but with a bit of luck, one should be able to compute these flux laws. There's a twistor action for full Yang mills, not just for the self-dual sector, and we should be able to compute how the flux works. And also one would like to see some physical meaning for it so that you could actually sort of relate to sort of things that other people, I think, at least today, are talking about, which I think connect to sort of more real physics about sort of how gravitational radiation is manifested at null infinity. Anyway, so what we've managed to do is we managed to sort of get a much more compact formalism. We now understand where the complexities in the Friedel-Pranzetti-Reclario formalism is coming from. And these correspond to the sort of expansion of these frames at null infinity. And but it also gives an alternative derivation of the Castello-Paquet sort of celestial CFT. So the J and J tildes can now be represented at null infinity, or at least spatial infinity, the limiters you go out to spatial infinity of these formulae. So this really fills in, I think, a lot of gaps in our understanding as to how the different ideas fit together. So, okay, so we've seen that celestial algebras then are symmetries of self-dual sector that are acting locally on twistor space and not really on null infinity now. And you know, are these like then a 3D analog of Virasoro for integrable celestial CFT threes? But I think the real question is, can we see these acting on the S matrix in a sort of a very constructive way? So we're still sort of a little bit short of that. I mean, for somebody from the amplitudes community, a lot of this stuff looks like inverse soft factors. And we know we need to go beyond that to get the full amplitude, although you can get quite a long way. And the other part of the story here, which we've yet to make contact with, is that, of course, there are these complete, formally for scattering amplitudes, at least at tree level, with results for the loop integrand at loop level as well, from twistor strings and from ambi-twistor strings. And these one would like to see some unification between those theories. The reason why those theories are difficult to sort of incorporate into this framework is because those theories have a world sheet that's at least at tree level, but that world sheet is no longer the celestial sphere beyond MHV. So for the MHV amplitude, it is the, you know, these things all coincide, and but beyond MHV, it's not so complicated. I mean, there's still a geometric relationship. They're multiple covers. So there's obviously a route forward there. We should be able to just push down the twistor strings or ambi-twistor strings to get celestial speeds. But anyway, that's a work for the future. So I'll stop there and say thank you. But before we go on, I did want to advertise. I don't know if maybe Andrea's already gone home, actually, but there is a special focus issue of classical and quantum gravity, asymptotic symmetries, conserved quantities, and flat space holography. This is its URL, and we've already got a few articles there. But anyway, if you've got something you're really proud of, do send it into that. So thank you very much.
Thank you, Lionel. Are there questions? Marius?
Thank you. Yes, what do you have exactly in mind with the celestial CFT3s?
Well, okay. I mean, I was saying this with at least 3 different hats on, I think. So this could be a Carolian CFT3. You know, 2 + 1 Carolian. It could be a. I mean, well, they're already part of the furniture in celestial CFTs. But I was also actually sort of thinking a little bit about the fact that these things have extension to cases where there's cosmological constants. So the algebra shifts a bit, it deforms, but not by as much as you might have thought. So there's also hopes of being able to do things like this in ADS4 or Decissa4. So these algebras will be there. What you do with them and what their relation to the physics is still unclear.
I have a question. If you could go back to the slide where you show mu in terms of this time direction, t. Yes. So this is not the incidence relation, right?
No. This is just explaining that the twistor space fibers over null infinity.
Right.
So and it sort of depends a bit. I mean, this one here is related to a spherical Bondi gauge.
So would this be true in curve space-time, or sorry, in curve background?
Absolutely, yeah. So, yeah, no, that is absolutely true in curve background, yeah.
So, okay, but we don't have a time direction in curve background. Sorry, not a.
Well, this T alpha dot is just meant to be the time-like vector associated with choosing a spherical metric on the sphere. So,
I see.
And in fact, if you use a planar gauge, planar Bondi gauge, you'll get a formula that doesn't have the lambda bar there, but just the kind of iota direction at infinity, which is actually rather nicer. So in our paper, we didn't use this gauge. In our paper, we used the planar Bondi gauge rather than the spherical Bondi gauge.
So is there any abstraction to do it in curve background?
Sorry, is
there any abstraction to put the twistor action in curve background and compute the charges?
This is all understood on a curved background. So all of these formulae were working on a curved background. I mean, it's one of those things you see when you're at null infinity, that the self-dual part and the anti-self-dual part are separated off. So you can't tell whether you're in the self-dual sector or whether you're in the full sector. You still have both pieces of data there in the twistor action. It's only when you evolve into the bulk that you will start to see a distinction between the self-dual and the full theory. And this is all curve space, and that's what leads to the complexities of these formulae, because you've not only got the A there, which is reflecting the curve background, but you've also got all of these kind of du inverse A's and du inverse squared A's and these double commutators and so on, coming from the fact that you've had to integrate for the F this kind of holomorphic frame or parallel propagator. So this is very much curve background in that sense.
Can I ask, when you mentioned the relationship with Costello packet G tilde, you said there was no natural space-time interpretation. Did I got that right? Is there?
Well, you could, yeah. I was maybe being a little bit sort of rash there. I mean, in the first instance, no. But on the other hand, if you go back to where we have where we go to scry and have both an A and an A tilde, so the A tilde is obviously the ASD part. So you could think of these as having separate gauge transformations associated with them, and then I think we could perhaps associate the gauge. So you have gauge transformations in the self-dual A that could have its own independent ones, and I think those could be interpreted as once you go out the hierarchy. I think those. So I was trying to say twistor theory is better because you see things you don't see on spacetime, but I'm sure if you're cunning enough, you could see it on spacetime.
Great. I don't see any more questions. So before we go for lunch, please, I remind you to sign up on this sheet of paper on the table if you want to participate to the guided tour. Let's give a hand to Lionel for the talk. Thank you.
Thank you.